have a mass spectrometer. There's a sort of a capacitor right here, and that's what accelerates the charge through a voltage. And so let's say it's a proton here, it's repelled from the positive, it's attracted to the negative, and then there's a little hole in this plate so that it fires through here where it enters a magnetic field. And the magnetic field is represented by these red dots. The red dots are supposed to be like an arrow pointing out of the screen. That's the direction of the magnetic field. We talked about this type of problem in class a long time ago now. But if you remember, charges that enter into a magnetic field like this, where their motion is perpendicular to field, will go into circular motion. And in class, we derived this formula for the radius of the path of the charge when it goes into the magnetic field. In the formula, r is radius, then we have the mass of the particle, the voltage that it was accelerated through, so whatever this number is here, so the 2876, the charge of the particle, and the magnetic field strength. So you plug all those numbers in and it calculates the radius of the path. Okay, so this problem has two parts. The first is to figure out the radius, and so I plugged in the numbers for the calcium plus ion using the data on the table here. So it has a mass of 0.666 times 10 to the minus 25 kilograms. The voltage is this number, 2876. The charge, it is a singularly charged ion, so it's 1.602 times 10 to the negative 19, and the magnetic field strength is 0.652 Tesla. So you plug in those numbers and the result is 0.0750 meters. Okay, so that's the first part of the problem. It's pretty straightforward. Plug into this formula. The second part of the problem, the way I thought would be most efficient to do it was to take the data that's here and to put it in an Excel file. So I have the same data plugged in over here. And if you'll notice, there's a third column of data for mass over charge. So the first is mass, the second is charge, and then we have mass over charge. And that's because of the formula. The voltage for every particle is going to be the same. The magnetic field will be the same, but they have different mass and charges. The bigger the mass to charge ratio, the bigger the radius will be. So if I make this table in this way, I can calculate what the mass to charge ratio is. And then I guess the most efficient way to do this would be, let's see, I'll highlight the table. Come on, drag it over. Let's sort it. Custom sort. And we'll go from smallest to largest. Okay, put that back. All right, so now in the spreadsheet over here in the spreadsheet table, it's ordered them from the smallest mass to charge ratio to the largest. And that, according to the formula, means the smallest radius to the largest. So then I can put the particles with their appropriate path. All right, so there was a question about this problem, question 4 on the homework, and there was also one about question 6. So let's take a look at question 6. All right, so this one here is about the law of induction. And so you have a formula for that. I believe the question was about the second part. So I'm going to assume that you know how to calculate the magnetic field from the formula for Faraday's law. And so that formula involves essentially the voltage, right? And then the magnetic field, the area of the coil, or in this case the solenoid, and the time, because it's the rate of change of flux through the solenoid that determines how much voltage there is. Okay, so we know what the voltage is. It's this number here. We know that the area is 4.5 centimeters squared, or the change in area is 4.5 centimeters squared. It changes in 1.5 seconds, so that's the time. And that leaves one unknown, which is the magnetic field. So you solve for the magnetic field, and it happens to work out to be 1 Tesla. The second part of that, which is where I think the question was, is now you have a practical constraint. The largest magnetic field that the solenoid can actually produce is only 3.5 times 10 to the minus 3 Tesla. And so the key here is realizing that the field strength of a solenoid is just proportional to the number of loops. So if the solenoid can produce a field of this many Tesla, then you can just add more loops to it, and each one would be multiplying the amount of flux. So if the field of a single solenoid can only be this big, having multiple loops multiplies the flux. So really the problem boils down to how many times this number equals this number. So n times 3.5 times 10 to the minus 3 equals 1. And if you do the math out for that, solve for n, you get 1 divided by 3.5 times 10 to the minus 3 equals 286 loops. So if there are 286 loops, it will magnify the flux 286 times and essentially magnify the field 286 times. Okay, I think that's all the questions I got on